Welcome to the new lesson in physics, that is LC oscillations. The phenomenon of LC oscillations is observed when a fully charged capacitor is connected to an inductor through a key as shown. Now consider a fully charged capacitor with plate A positively charged and plate B negatively charged connected to an ideal inductor of inductance L. When the circuit is closed, the capacitor discharges through the inductor. That means when the capacitor gets discharged, it sends a current through the inductor. The current is from A to B through the inductor outside the capacitor. As the time goes, the charge flowing in the circuit increases and the current in the circuit also increases. So when the capacitor gets fully discharged, the current in the circuit will be a maximum. When the charge on the capacitor becomes zero, the current through the inductor, it starts flowing in the same direction because of the property of inductance. We know inductance is the property by which a coil opposes a growth or decay of current through it. So when the capacitor gets discharged completely, the current actually it should drop to zero. But the inductor, by the property of inductance, it continue to send the current in the same direction. With that current, the capacitor gets charged in the opposite direction. That is, now plate B becomes positive and A becomes negative. As the capacitor gets charged, the current in the circuit decreases. Finally, when the capacitor becomes fully charged in the opposite direction, the current in the circuit becomes zero. Now, the capacitor gets discharged in the opposite direction. That means the capacitor starts sending current in the opposite direction, that is from B to A through the inductor outside the capacitor. Now, when the charge on the capacitor becomes zero, current is maximum and the magnetic field around the inductor also is maximum. By the property of inductance, it sends current in the same direction. Because of that current, the capacitor gets charged in the opposite direction. That means A becomes positive and B becomes negative. As we discussed earlier, because of this charging, the current in the circuit decreases and charge on the plates increases to a maximum. Again, when the current in the circuit becomes zero, the charge on the capacitor will be maximum, and at this point the capacitor starts sending current in the opposite direction. That means it gets discharged, sending a current through the inductor in the direction from A to B. And the same processes as we discussed earlier, it repeats. So in this circuit, the changes in the current and the changes in the capacitor charge are oscillatory in nature. That means it increases and decreases. Let's obtain expression for those charge and current. At time t equal to 0, the charge on the capacitor is maximum and let it be Qm. And the current in the circuit, it is equal to 0, and the induced EMF across the inductor also is equal to 0. Now at any time t, the charge on the capacitor, let it be Q. Therefore, the potential difference between the two plates will be Q by C, where C is the capacitance. Now, the potential difference across the inductor, that is the induced EMF, that is L into di by dt. Now, applying Kirchhoff's law to the loop, we have Q by C minus L into di by dt is equal to 0. Let it be equation 1. We know in this circuit, as the charge on the capacitor decreases, the current through the inductor increases and vice versa. Because of that, we can write I is equal to minus dq by dt. Therefore, the equation becomes q by c minus L into d by dt of minus dq by dt equal to 0. That is q by LC plus d square q by dt square equal to 0, or in other words d square q by dt square plus q by LC is equal to 0. Let that be equation 2. We know when an object is in oscillation, if the oscillations are simple harmonic in nature, then representing the motion, we have the mathematical equation d square x by dt square plus omega 0 square x is equal to 0. This is the differential equation which represents a simple harmonic motion. And we have the equation d square q by dt square plus q by LC equal to 0, which is similar to equation 3. In equation 3, omega 0 equal to root k by m. Now comparing equations 2 with equation 3 term by term, we know q takes the place of x and 1 by LC takes the place of omega 0 square. So by comparison, we have omega 0 square equal to 1 by LC or omega 0 equal to 1 by root LC. The general solution of equation 3 is x is equal to a cos omega 0 t plus phi, where a is called the amplitude of oscillations, which means the maximum displacement. Omega 0 is the angular frequency of the oscillations and phi is the initial phase. So in the same way, we can write the solution for equation 2 as q is equal to qm cos omega 0 t plus phi. Here qm is what we call as amplitude, that is the maximum charge. Here it represents maximum charge. That is at time t equal to 0, q is equal to qm. So using that, we have qm equal to qm cos phi, just substituting t equal to 0, which indicates that cos phi equal to 1 or phi is equal to 0. So our expression for q becomes qm cos omega 0 t. That means phi is equal to 0. So that is the expression for charge in the circuit. When a charged capacitor is connected to an inductor, the charge in the circuit is given by q equal to qm cos omega 0 t. And I is equal to minus dq by dt we have already taken. So by differentiating, we have I is equal to minus d by dt of qm cos omega 0 t. Doing the differentiation, we will get I is equal to omega 0 qm sin omega 0 t, or I is equal to Im sin omega 0 t, where Im is equal to omega 0 qm. So we have obtained the expressions for the charge in the capacitor and the current through the inductor, which are oscillatory. From the equation we can say both are oscillatory in nature. Now, at any instant of time, the charge on the capacitor is given by q square by 2c and charge in the inductor is given by half Li square. Now, in this equation, we know q is equal to qm cos omega 0 t and I is equal to Im sin omega 0 t. And we know omega 0 is equal to 1 by root Lc and Im is equal to omega 0 qm. So, in the expression, we have omega 0 equal to 1 by root Lc or omega 0 square equal to 1 by Lc. So, from that we can write an expression for L as 1 by omega 0 square C. Now, the total energy in the system, we can write U total is equal to U plus U dash, where U is the energy stored in the capacitor and U dash is the energy stored in the inductor. So substituting, we have Q square by 2C plus half Li square, that is equal to, substituting, we have Qm cos omega 0 t whole square by 2C plus half 1 by omega 0 square c into Im sin omega 0 t whole square. There we substituted for L. Then again doing the substitutions and simplifications, we have the total energy equal to Qm square by 2C into cos square omega 0 t plus sin square omega 0 t, which is the same as Qm square by 2C. That means the total energy stored in the system is Qm square by 2C. Initially, at time t equal to 0, this energy is stored in the capacitor in the form of electrostatic potential energy. And as the capacitor discharges, the energy gets stored in the inductor also in the form of magnetic potential energy. That means when the capacitor gets discharged through the inductor, the energy is partially electrostatic and partially magnetic. This system of charged capacitor and inductor is similar to a system of horizontally mounted spring. That means a tiny mass m connected to a spring. When the spring is compressed from its original position, we know that energy is stored in the spring in the form of potential energy. When it is released, that energy manifests itself as kinetic energy. So there is transformation of energy between potential and kinetic as the mass moves between the extreme positions through the equilibrium position. In the same way, the energy undergoes transformations between the capacitor and the inductor in the form of electrostatic potential energy and magnetic potential energy. In the beginning, when the capacitor is fully charged, the energy is purely electrostatic, and when the charge on the capacitor becomes zero, the current in the circuit becomes maximum and the energy is fully stored in the inductor in the form of magnetic potential energy. At any other instant in between, we can say that energy is shared by the capacitor and inductor. That means energy is partially electrostatic and partially magnetic. This table shows the analogy between electrical system and mechanical system. We can see that the inductance L in the electrical system is analogous to mass m. Likewise, the reciprocal of capacitance, that means 1 by C, is analogous to force constant K of the spring. And the charge Q is analogous to displacement X. Electromagnetic energy is analogous to mechanical energy. And the current I is analogous to velocity dx by dt. And the expression for total energy, it becomes half q square by c plus half li square, which is the same as half kx square plus half mv square in the case of a loaded spring.